Hey, what's going on, fellas? I got to do a quick video tonight here for T-Dog over in Africa. They're having a heck of a time with their D-tank. They're trying to do some fractional distillation of some tired of fuel diesel. And I'm going to use this quick diagram to kind of describe some of the problems that are happening and one of the solutions for it. We initially discussed the possibility of using an oil transfer system. I don't know if I like that idea for several reasons. First of all, the oil transfer fluid costs thousands of dollars. It's like $10,000 for 1,000 liters, and you can burn it up accidentally. So we could ruin $10,000 worth of heat transfer oil if we're not careful. What we're looking at here is a diagram that's going to describe some of the problems with the process of distillation of pyrolysis byproducts. So typically what happens whenever you're distilling any type of fuel or dirty sludgy material, like for instance paint thinner, which I have done a lot of, you end up with this bottom layer on the bottom of the beaker when you're doing that. I did some experiments a while back where I was trying to reuse some engine cleaner. It was some denatured alcohol, and I was rebuilding a lathe. And during that process of rebuilding that lathe, I was using so much solvent that I decided to boil some of the dirty solvent in a flask. And every time you would get this layer of material on the bottom, this very dark black layer of crap at the bottom of the beaker. And that would cause an insulative activity to take place. And because it would start to insulate, you would get these explosions of bang boiling. I don't know what the actual technical term for it is, but you would get a bubble that would begin to form, and then it would collapse, and it causes cavitation, which could actually crack the bottom of the beaker. It can also eat holes in the bottom of a tank. So this bottom layer is a huge problem. No matter what you do, the more heat you add to it, the more sludge that builds up, and over time it turns into a hard rock at the bottom. And what that does is it allows the bottom of your D-tank to get so hot that it begins to degrade at a far higher rate than it would if this sludge layer wasn't here. So let's talk about flame impingement for a second. When a flame directly hits metal in a boiler system like this, the research that I have done on the subject indicates that a fluxing action takes place when unburnt fuel. Let me draw a small sub-diagram here. You've got a plate of steel here, okay? And one of the things that's protecting it is a small oxide layer on the surface, whether it be rust or whatever. It slows down the speed of this piece of metal just rusting to nothing. So if you take a flame and you blast it right on there, what happens at this interface, the interaction between the flame and the metal, is a fluxing action that removes that oxide layer, exposing a continual new layer of metal that is eroded away by a high temperature and the fluxing action of the fuel. Not to mention the fire that we're aiming on this thing is a product of this distillation system that is a very high sulfur content fuel, which just totally adds to it, tenfold. That sulfur stuff is very corrosive. So that's an issue. So one way we have to mitigate that is we have a flame tube going through the boiler. This is a very common process. A flame tube is a very known industrial piece of equipment, and it usually has an extractable section that can be removed from the system before it becomes completely destroyed and replaced during an outage or any other cleaning that needs to be done on the bottom of this tank. Another benefit of the flame tube is that we get all this heat coming up, boiling the fluid, and the sediment is falling down in the bottom of the tank, and it's not affecting this heat tube. What I've drawn here is a fuel manifold that sucks fuel from the bottom of the tank above the sludge line, I might add. You could have it go way up here actually if you wanted, or some. I'd recommend that it be just below the heating tube. and that extracts fluid from the tank to a pump and throws it back out these rails and blasts this section of the pipe with high turbulent flow of fuel. And what that would do is reduce the buildup of any gum or varnishing that might take place. And it also helps keep this section of tube cooled down a little bit better in the sense that it's not getting bubbles forming on it. When a bubble forms on this material, not only does it reduce the convection of heat to the work zone, but it allows it to get hotter than it normally would. So we're going to knock those bubbles off with turbulence, and that's going to help us move that heat around. The bubbles will be smaller when they're knocked off. They won't be allowed to grow as big. We will still have bubble production, but it won't be as destructive to this piece of pipe. Now, at the end of this piece of pipe, the gases are going to hit a T that has two ports sticking out each side of the tank. And as you can see, the way those gases travel, they hit an outside wall, and then they are distributed throughout the exterior of this tank and vented out the outside, so we don't have any insulation issues. We could also make an insertion tube that simply slides into this, runs for a while, and can be slid back out. I recommend an extraction section like this. This tube can be made out of square metal, square 1/4-inch steel. I know you guys got some manpower, and it looks like you guys have a great welder on hand. I've seen some of the weld beads the guy who built the burners did. It looks really nice. So this is just idea number one, and I wanted to use it as a kind of a description. Another thing we have to remember about the distillation process is as it progresses, the temperature or boiling point increases. Never want to let it get too far gone. And once we get it to the point where it needs to be at 350 or 300 degrees Celsius to boil, it actually needs to be extracted from this tank and put in a smaller processing tank that runs under vacuum. That's standard procedure for a chemical process of this nature. I know you guys are very limited. You're out in the middle of a desert, for crying out loud. So forgive me if I'm asking for you to turn straw into gold there. But let's get this out of the way. We're going to talk about the next deal. And that is going to be the fractional distillation tower connected directly to the pyrolysis system. So you've got your pyrolysis unit here. You've got some hot gas, your expansion joint. And we would vent this gas into a container that has a stack, okay? And we would have these little things in there. Now, this is very abstract. There'd be 100 of them on there probably. Maybe not 100, but at least 20. And what would happen is they're stacked like this. And as the tower gets taller, the boiling point of the material is lower. For instance, this would be the, say, 300 degrees Celsius zone. So in this first layer, the gases coming out of this pyrolyzer here would come up, vent out, and turn into a liquid in this first area. And that liquid would go just beyond the top of these, and the rest of the gas would bubble out of this region. And that is why this is called a bubble cup fractional distillation tower. So the bubbling gas comes out. This liquid here is 300 degrees Celsius now, but it's a very heavy oil. The next tower up may only be 250 Celsius. And it is a completely different substance. And you have tap tubes coming off the tower as you grow. Let's say we're at the top now, and we're at 180 Celsius, which is the lightest oil you get off this process. This is the good stuff. And you would have maybe 12 of these things stacked up. Maybe you wouldn't need that many. I haven't experimented with this fuel. But this would eliminate the damn D-tank altogether. We just used a hot pyrolysis feedstock, run it directly into a fractional distillation bubbler cup, column, whatever you call the thing. I don't know what it's called anymore. I saw this thing when I was like 12 years old, so it's been a minute. But I'm pretty sure it's called a bubbler cup fractional distillation tower. That's what my 12-year-old memories tell me anyway. It was in one of those really cool old chemistry books that got like the thin, shiny magazine paper that you'll never see again. Okay, the next idea was the heat transfer fluid. I totally hate this idea. First of all, it's about $10,000 for 1,000 liters, or some of the prices I saw. I also saw $700 for 5 gallons of this stuff. We probably need 1,000 gallons easy. So that's a terrible idea. There's two things that can happen to this oil. If oxygen gets into it when it's, 420 Celsius, it gets this carboxyl acid buildup that just destroys the system. So you got to have an inert gas layer over the expansion tank. If you get it over 420 degrees Celsius or so, you destroy it. And we all know how temperature specifications and regulations work out in the desert. We need something that can just be beat to death. Like you almost need liquid metal. But if you guys do want to entertain the idea, I don't like it for the simple fact that we're at 450 Celsius is about the highest temperature for a good thermal fluid that I've seen. Some of them go a little higher. I think I did see one silicone one, but the stuff is just so crazy expensive that it's nuts. So, all right, let's draw the damn machine here. This is what we got. This is how you make a very quick plate heat exchanger. Man, I can't think here. Okay, here we go. This is a flat stock piece of 1/4-inch steel. Okay, and what we would do is we'd lay that out, and we would take, say, some 1.5-inch strips of 1/4-inch steel and put some walls on this bad boy, like so. You probably already see where I'm going with this, but let's get her done. Damn, that's too small. All right, something like that. And then what we would do is we have an intake port here. We get our connector on there. And we would take another one of these 1.5-inch steel slats, and we would throw it in there like this. And we would just tack weld it periodically. And we would not let it go all the way to the end. Okay. And at this end here, we would take a piece of that 1.25-inch material and we would make ourselves a loop. Just bend it like this. Okay. And then stop it before it gets all the way where it's going. Okay, so I think you can see where I'm going with this. And we put in these slats. Now these are tack welded on the bottom with a good little bead every 6 inches. Man, I'm having a heck of a time. And essentially, this is the gist of it. Now we would have this curved piece in each one. Like for instance, this one here would curve this way and all that. We don't want it to hit a flat wall. We would have a curved piece of stock in there. And the transfer fluid, and then we would take a flat piece of steel and throw it on the top of it. But that top piece would have holes drilled in it strategically so that we could put a tack bead, a button as I call it, every 8 inches to grab the top of that 1/4-inch piece of metal. Because this transfer fluid's kind of hot, stuff might start warping and buckling on us pretty bad. Maybe not, but better safe than sorry. That'll also keep it to where it can hold pressure. In case even just a few PSIs could bow this thing out a little bit when it's this big. So this would be about 2 foot wide, and you can maybe make it, 8 foot long or something like that. So we got transfer fluid pumping through this thing now. And it's going to loop through it like this. And we would have our discharge tube on the outside of it. Okay, so this is how you make a quick desert style plate heat exchanger. If you guys need a better diagram than this, if this isn't really inspiring you, then I can do better, but this is the gist of it. This is supposed to get you thinking. So what we would do in our D-tank, I'm going to give us a front view of the D-tank, is we would take these things and we would stack them in the D-tank like this. You're probably going to need a lot of them because I'm telling you guys, 100-degree temperature junction sucks. That is going to be terrible. Think about it. With fire, you've got like a 900-degree temperature junction. So it's not going to be boiling like crazy with this. So here's your fluid, and you've got these things in here. Of course, they would be supported by some kind of struts or legs or something. I don't know if I'd let them sit on, you could probably just let them sit on the bottom of the tank, but I don't like that because you're going to have that sludge layer. We want to keep any surface out of that. So you could technically just drop them on the bottom of the tank. We're in the desert, for crying out loud. We got to get this done. So that's how you heat the inside of the tank. I don't like the fact that we're just going to use the firebox as an insulation canister, though, if that's how we're going to do this. I'm not sure what type of insulation you guys have in that thing. Maybe it is okay. I haven't seen it. But this method, this very small temperature junction, is of such that it could allow more heat escaping this tank than we're able to put in it due to the heat capacity of this fluid, which is about 1.8 kilojoules per kilogram, which is terrible. Water's like 4 point something. To put it in perspective. Okay, so the same thing when we go to heat the fluid, we just take 4 of those units and we stack them like this in a box. Okay, this is a terrible drawing, but you got your burner here. Like I said, it's like midnight. It's already tomorrow, and I'm still up today. Okay, we got fire going into this thing, and it can just burn the crap out of it. And because the fire, if it isn't actually touching the metal, we're not getting that fluxing action. So what we would do is put a sacrificial box here. This would be a fire brick material here. If you got, I know you're in the desert. I tell you all these fancy things like we're going to put gold rims or gold doors on the crapper here. So that's kind of what you would want to do. This is your little heat transfer things I just showed you how to do. And the other option to get away from that heat transfer crap is just a standard old, there's your D-tank. There's your fluid. Okay, and we've got a big old tank of boiling water here. Okay, it's just boiling away, producing some steam that we then pump through a steam superheater coil. Got the fire there that burns up. Like we said, we don't care if we burn up this superheater coil. We'll make a real nice box, fancy box steam superheater coil that then shoots this high temperature steam into the same little things that we showed you, the little boxes where it just kind of travels through there in a loop or whatever. You can do spirals, whatever you want to do. Superheated steam gets us out of having to worry about damaging the thermal fluid. I know water's kind of hard to come by in the desert, but it's a lot cheaper than $1,000 a liter for or for 100 liters, whatever, of the thermal fluid. So, oh, I forgot. We would have another burner down here, of course, getting the water boiling in the water boiler tank, and that would give us the steam, which we would then superheat with another burner that's heating this coil, or it could be those box things that I showed you. Kind of give you, let me give you a or a face diagram of the plate heat exchanger. So you've got your big plate of 1/4" steel. You've got your input port. We're going to take let's say 1/4" tall slats, weld them all the way around this thing, so it's now a little like cigar box. Then we take a slat here and we stop it short. We take a slat here and we stop it short. And we're going to repeat that. This is an abstract. In reality, we would want to take a piece of the stock and put a U in here like this, because the